Hi there, this is Electric Fields 6, Electric Field Strength, part of the A-Level Physics. To start with, let's have a go at this question. So this is on electrostatic force and gravitational force from previous lessons. So if you want to pause and have a go at answering A, B, C or D, and then I'll explain how you do this. So we've got electrostatic force divided by the gravitational force, so the electrostatic force equation, which we've used previously. Now the one that I use is K Q1 Q2 over R squared. But in this instance we can't use K because K is 1 divided by 4 pi epsilon naught, and that's actually being used for this answer. So electrostatic force is charge 1, charge 2 divided by 4 pi epsilon naught R squared. The charges we will swap for E in the next step. And we're going to divide by the gravitational force. And the gravitational force is G M1 M2 over R squared. Then what we can do is flip this and bring the R squared up to the top. And then we'll change the letters. So Q1, Q2, we can call that E because it's charge E. So that E times E would be E squared divided by 4 pi epsilon naught R squared multiplied by R squared divided by G, and it's M1, M2, but the masses are the same, each of mass, so I'll call that M squared. As you can see, the R's cancel, the distances, and we're left with E squared divided by 4 pi epsilon naught GM squared. So the answer is D. Hopefully that went okay. So electric field strength. So previously we've had F equals, I'll use the full version, so Q1, Q2 divided by 4 pi epsilon naught R squared. And we've also got F equals EQ, both from previous lessons. And all I'm going to do is make them equal to each other. So I end up with EQ equals Q1, Q2 divided by 4 pi epsilon naught R squared. Q's cancel. So electric field strength is equal to Q divided by 4 pi epsilon naught R squared. Electric field strength from uniform fields is measured in newtons per coulomb or volts per meter, and it is a vector quantity. So if you want to make some notes on that, please pause, because I'm going to remove that now. And the way that I use this equation, remember, I do the 1 over 4 pi epsilon naught equal to K, which is 8.99 times 10 to the 9. Mathematicians, I'm really sorry that I've done an equals symbol than an equals. I know that's not proper, but never mind. So electric field strength can be written as simply KQ over R squared, which is the format that I like to use. Okay, let's move on. Let's utilize this. So, really simple question. If you want to pause and have a go. Calculate the electric field strength 25 centimeters from a point charge of 40 microcoulombs in a vacuum. Epsilon naught is given. So I'm going to do E equals KQ over R squared. You can do 1 over 4 pi epsilon naught if you wish, completely up to you. K is 8.99 times 10 to the power 9 times the charge. The charge that we're looking at is the 40 microcoulomb charge, so 40 times 10 to the minus 6 divided by distance squared, 25 centimeters. So we've got 0.25 meters squared. So that gives an electric field strength of 5.8 times 10 to the power of 6 newtons per coulomb, or volts per meter. Okay, let's move on. A couple more questions, so if you want to pause and have a go. So I'm going to calculate the electric field strength 2 centimeters away from a point charge of plus 6 microcoulombs and 4 centimeters away from a point charge of minus 12 microcoulombs. So I'm going to do A first. So electric field strength is KQ over R squared. So we got 8.99 times 10 to the 9 multiplied by the charge, which is a plus 6 microcoulombs times 10 to the minus 6, divided by R squared, so 2 centimeters. So 2 centimeters is 0.02 meters, and then square it. 1.34 times 10 to the power of 8 newtons per coulomb. Make sure you've got that down. I'm going to remove it and do B. So B. So same equation. KQ over R squared. Put the numbers in. So 8.99 times 10 to the 9. Times the charge this time is minus 12 times 10 to the minus 6 coulombs. Divided by 4 centimeters, so 0.04 squared. So that gives an electric field strength of minus 6.74 times 10 to the power of 7 newtons per coulomb. So a positive answer just means that the field would repel a positive charge, and a negative answer means that that field would attract a positive charge. So negative is attractive, the positive would be repulsive. Let's move on then from there. One last question to practice. One thing that we need to talk about though is this bit. So the mass of a nucleus of an isolated copper atom is 63 U. Now the U value for mass will be on many data sheets for A-level physics, regardless of examination board. So what I'm going to do is just share that value with you initially. So the U value is equal to, so we've got 1.661661 times 10 to the power of minus 27 kilos. And U is known as the atomic mass unit. You'll come across it more specifically in nuclear physics. So if you want to have a go at that question now, and then I'll take you through the answer when you've done. So let's do electric field strength first. So the electric field strength is KQ over R squared. So K is 8.99 times 10 to the power 9 times the charge. Now the charge is 29 E. So that would be 29 times the charge of an electron. 1.6 times 10 to the minus 19. And then we need to divide that by R squared. And we need to be careful because we've got the diameter of the atom. So 2.3 times 10 to the minus 10, we need to half that to get the radius. So that would be 1.15 times 10 to the minus 10 squared. And if we pop that in our calculator, we'll get 3.15 times 10 to the power 12 newtons per coulomb, or volts per meter. Now, if you've already covered gravity, which you should have done, because typically you would do gravitation before electric fields, we can then calculate the gravitational potential at P due to the nucleus. So let's just make some room. So gravitational potential, this is good for revision. So that's minus GM over R. So we got minus 6.67 times 10 to the minus 11, multiplied by the mass, which is 63 times the U value, which we gave as 1.661 times 10 to the minus 27, divided by the radius. Now again, the radius is half the diameter, which is 1.15 times 10 to the minus 10. So that will give us a gravitational potential of minus 6.07 times 10 to the minus 26 joules per kilogram. So 6.07 times 10 to the minus 26 joules per kilogram. Hopefully that went okay, and I'll see you for the next one. Cheers.